So far we have considered a thermal interaction where we have the external parameters of the system fixed so that the energy levels are not changing, but the probability of occupancy of these energy levels, existing energy levels, are changing. Now we will consider the most general case, a thermodynamic interaction that involves the performance of work, which means external parameters of the system are changing, as well as the exchange of heat as in the thermal interaction. So this will complete the theory of statistical thermodynamics. So a general thermodynamic interaction will involve work as well as exchange of heat. So we can basically formulate this by saying involving changes in external parameters that results in work done on the system and exchange of heat. So that's thermal interaction. So this basically completes the theory of statistical thermodynamics. So the first law of thermodynamics, remember, tells us the change in the mean energy of the system is due to heat added to the system and work done on the system. So it's Q plus W. So in the case of general thermodynamic interaction, we have both of them playing a role. So in order to discuss the dependence of the number of states on the external parameters, we're going to consider a macroscopic system characterized by one or more external parameters such as a volume V or the applied magnetic field B. So let's say that we have a macroscopic system that has an external parameter I'm going to call X. For example, this could be volume of the system, volume V. It could be external magnetic field B, etc. So we can give many examples. Now, when you have a change in the external parameter of the system, remember that changing the external parameter of the system, delta X, leads to a change in energy levels. Energy levels will shift. Example, the energy of a spin in a magnetic field, if the spin has a magnetic moment mu 0, it is minus mu 0 B when the moment is aligned with the external field, and as you can see, as B changes, the energy level of the system changes. So it basically affects the energy levels. Now we call omega as a function of E and X the number of Uh, quantum states these are accessible quantum states in the energy interval E to E plus delta E. And this number of accessible states to the system also depends on the external parameters of the system X. So that's basically what I would like to find out, how the number of accessible states changes with the external parameter X of the system. Now, in order to demonstrate this, I'm going to consider as an example an ideal gas in 3 dimensions. So this is a system we have considered before. So ideal gas in a 3-dimensional box. So for this system, we have used arguments based on the volume of one molecule and the number of different ways we can put the molecules inside this box to find that the number of accessible states can be written as the total volume divided by the volume occupied by one molecule to the power n, where V0 was volume of one molecule and V was the total volume. So as you can see here, omega is a function of V, that is the volume of the system, which is an external parameter of the system. So the number of accessible states does change with the external parameter of the system. Now, using quantum states for this system, we have calculated the density of states, and we have found out that the number of accessible states for energy in the range E to E plus delta E was given as so I'm going to modify this, and it depends on energy as well as volume. So X is volume, is given as V divided by 4 pi square H bar cube 2m to the power 3 over 2 e to the 1/2 delta E. So this is also a function of V here. So it's important that we see that the number of accessible states depends on V. Now, if you're wondering where this came from, so this is a calculation we did a while ago. This is basically density of states, rho of E, which is the number of states accessible for energies less than E, a derivative with respect to energy d phi dE, and omega as a function of E was the density of states multiplied by delta E. So this gives us the number of accessible states for energy range E to E plus delta E. And we can find this density of states using the energy levels of the system. So remember that the energy is given by h bar square k squared divided by 2m. It is a momentum squared divided by 2m, and the k values were quantized. So kx is, for example, nx pi over L for a box that has the same dimensions, a cubic box. Ky is ny pi over L. kz is nz pi over L. So we had for the energy h bar squared divided by 2m pi squared over L squared nx squared plus ny squared plus nz squared, and these nx, ny, and nz are integers starting from 1 going up to infinity. And if you want to know the number of accessible states inside a certain region, you can think of this in n space, nx, ny, nz. So you have discrete values for nx. So we have nx, ny, and nz. And basically nx squared plus ny squared plus nz squared we call r squared. So this is going to be forming 1/8 of a spherical region inside which we have all the states. So the states will reside inside this region. So we will see that the number of states for energies less than E, less than or equal to E, will be given by 1/8 times the volume of this cube, 4/3 pi r cube. So it's basically 1/6 pi r cube. So this was giving us our 2. 2, 3 is 6. And this r square, we can take r to be square root 2me multiplied by L divided by pi h bar. So L divided by pi h bar multiplied by square root 2me is r. So for the number of states that are accessible for less than energies E would be 1/6 pi L cube over pi cube h bar cube 2m to the power 3/2 energy to the power 3/2. So L cube is the volume of the box V. So this pi gets rid of this 3, makes it a square. So for the number of states below energy E, we have 1/6 V over pi square h bar cube 2m to the power 3/2 e to the power 3/2. And for the density of states, we have d phi dE. That gives us the number of states per energy range dE. We will have a 3/2 from the e to the 3/2. So this will give us 1/4. So v over 4 pi square h bar cube 2m to the power 3/2 e to the power 1/2. So this is how we obtained the density of states. So if you remember, this is a calculation we did before. The quantization of k values came from standing wave solutions, because the wave function had to vanish at the boundaries of this container. We came up with this quantization of k values and standing wave solutions. So we find that the number of accessible states is indeed a function of V, the external parameter of the system. And if you look at the energies of these quantum states, So if I look at the energy of a certain quantum state, which is specified by the values of nx, ny, and nz, this is basically pi square h bar square divided by 2m L squared, nx square plus ny square plus nz square. Since L cube is equal to V, L square is equal to V to the power 2 over 3. So you can see that the energy of the art state of the system will be pi square h bar square divided by 2m to the power v 2m over v to the power 2 over 3 nx square plus ny square plus nz square. So we find that the energy levels are a function of the external parameter v. So let me note that here I have two important conclusions. So just to summarize, one important conclusion is that the number of accessible states for energies in the range E to E plus delta E depends on the external parameter V, and furthermore I found that each energy level is a function of V, as we have initially suggested. So if you want to find out the change in the energy level, DER, the energy level change due to a change in the external parameter will be del ER del X, because the energy level ER depends on values of nx, ny, and z, and it also depends on the volume V, the external parameter V. So when you want to find out a change in the energy level for fixed values of nx, ny, and z, this will be del E del X multiplied by dx. So that means the other parameters nx, ny, and z, the quantum numbers, are fixed. So I'm going to call this the variation of the art energy level with the external parameter x, capital X sub r. So it's capital X sub r dx. So capital X sub r is defined as the variation of the art energy level with the external parameter x. So let's keep this definition for the rest of our discussion. So if you look at, again, if you go back to our three-dimensional ideal gas, you can see that the energy levels here are given by pi square h bar square divided by 2m v to the power 2/3 nx square plus ny square plus nz square. So for our example, x sub r would be equal to the derivative of E sub r with respect to x, which is, in this case, because x is volume, so what is the effect of changing the volume in the energy levels? Well, that is going to give you, because you have a power v to the power 2 over 3, or v to minus 2 over 3 if you put it in the numerator, the derivative will give us a minus 2 over 3 pi square h bar square divided by 2m. Now v to the power minus 5 over 3, it was 2 over 3, now it has become 5 over 3, nx square plus ny square plus nz square. So you can see that if I simplify this x sub r will be equal to minus pi square h bar square, because the 2's will cancel, divided by 3m v to the power 5 over 3 nx square plus ny square plus nz square. And my point is that the xr value, the variation of the energy level with x depends on the quantum numbers, so it depends on the state. So this is a function of nx, ny, and z. So we're going to get a different variation for different states. So the other conclusion I have is x sub r is a function of the state r. So it's a function of the quantum numbers n and x and y and z. So it depends on the state. All right. So we're going to continue with this discussion. So in the next video, so basically I wanted to highlight these dependencies in order to see how we can calculate the change in the number of accessible states of the system when you change an external parameter of the system. So we have found out in the because we're doing the general thermodynamic interaction where we have heat and work involved. So for the work part, you need to have an external parameter of the system changing, and that will change the energy levels that we simply remember from the spin system, where a spin with magnetic moment mu0 will have an energy level minus mu0b when its moment is aligned parallel to the field. The number of accessible states will depend on the energy as well as the external parameter x. So you can see that for ideal gas in a three-dimensional box without any limitation on the energy, the number of accessible states is v over v0 to the power m. That's something we have done at the beginning of our discussion in this course. And for the quantum treatment for three-dimensional box, we have found that the number of accessible states has an explicit dependence on V when it has an energy in the range E to E plus delta E, and that is given by the density of states multiplied by delta E, and the density of states we have found here to be V over 4 pi square h bar cubed 2m to the power 3 over 2 energy to the power 1/2. And if you remember, for 2 dimensions this is e to 0, for 1 dimension e to minus 1/2, etc. So the density of states depends on the dimension of the box. And so the energy levels that we see here, which are given by momentum squared divided by 2m, and taking into account quantization of k values, we have found that the energy levels depend on nx, ny, and z, as well as the volume of the box. So the number of accessible states for energies into range e to e plus delta E depend on the volume. The energy of each quantum state also depends on the volume. And when we look at the variation in the energy level when I change the external parameter of the system, keeping the quantum numbers the same, that is del ER del x multiplied by dx is equal to DER, because nothing else is changing, I have defined the variation in the energy level with respect to the external parameter x del ER del x, x sub r, so capital X sub r, and I have calculated capital X sub r for my three-dimensional quantum gas, and I find that this capital X sub r depends on the state that we're talking about. So nx, ny, and z values will determine how much the change in the energy level will be for the change in the external parameter. So x sub r is also a function of the state that we are talking about. And you can see that x of r is also a function of the external parameter x here. So it is because of this v to the 5/3 dependence that we can explicitly see in this expression.